Hi, and I'd like to thank the organisers for inviting me to speak at this conference, which is very exciting. And I would like to talk about coastal megagravel or coastal boulder deposits in general, how they can be used to decipher overland flow velocities during storm inundation, and how this can be leveraged to inform management of coastal heritage sites. And I'd like to acknowledge my collaborators in this work, some excellent students, Danielle Zentner, Kalajan, and Una Watkins in particular, funding from the National Science Foundation, without which this wouldn't have been possible. And the drone image that you're looking at here and a number of others that you'll see in this presentation were taken by Peter Cox. That image and others that you'll see were taken on the Aran Islands off the west coast of Ireland, which have spectacular coastal boulder deposits and also spectacular heritage sites, so the perfect place to look at these things in tandem. And to define the term megagravel that I used in the talk title, this is actually a technical term, perhaps my favorite technical term, and it refers to boulders with an intermediate axis that's at least 4.1 meters. This particular example here, which is on Inishmore, I refer to it as the dolmen block for obvious reasons. And it is about 5 meters long, 4.5 wide, and almost a meter thick. And this thing weighs about 40 tons. It's sitting here on this pile of other rocks, about 10 meters above the highest high water mark, AHW is above high water, and about 50 meters inland of the high tide line. And it was put here by waves. As another example, this one from Inishmaan. This piece is it's almost 12 meters long, 4.2 meters wide, just under a meter thick, and it weighs about 78 tons. And if we step back and look at that in perspective from the air, the arrow points to that same block there, 78 tons. It sits 17 meters above the high water mark, and it's 130 meters inland. And this aerial image gives you a really nice sense of how big a distance that is, and the amount of energy and the force of the waves that would have traveled across this platform to emplace that boulder and all the others in this boulder deposit. And there are some people here for scale. So these kinds of deposits record extreme wave events anywhere that they occur, and they occur in lots of different kinds of places. This is back on Inishmore, and at some intermediate elevations. These cliffs are about 11 or 12 meters high, but there are also sheer cliffs, as here on Inishmaan, where these things occur. And it is these cliff top sites that are of particular importance for the coastal heritage sites on Inishmaan. There are two main cliff top sites of importance, Dún Aengus, of course, and also Dún Dú Cathair, the Black Fort, which is where we'll be focusing most of the attention in this talk. These kinds of sites are obviously subject to wave action and erosion, and we can measure that by using aerial imagery combined with historic maps. Here you see the 1839 Ordnance Survey map, and these gentlemen were kind enough to map in all the field walls, which, as we look at this highly conserved landscape a century and a half later, we can see that many of those walls are still in place, and we can use those to precisely register the images so that the changes that we see at the coast we can be confident they are real. And in this case, the blue line shows the 19th century coastline superimposed on the 21st century image. And you can see that there has been up to about 25 meters in this case of retreat at certain points in the coastline. So there is active erosion going on here, but it's not simply undercutting and collapse because of wave action. It's also waves overtopping these cliffs and flowing as bores across the upper platforms, eroding, creating new boulders and transporting them as they go. On these cliffs here, which are next to Dún Dú Cathair and are about 25 meters above the highest tide level, you can see piled on the top deposits of boulders, and these particular ones include ones that are up to 5 tons or so in weight. And we can use these to think about how fast those bores were moving and how much force they were exerting. Another view here, you can see Dún Dú Cathair up there on its peninsula towards the top of the image. And here on the next headland over, you can see a lot of boulders, not much megagravel at these elevations, but still really sizable rocks. And the boulders towards the right of the image are darker gray. They're very weathered surfaces that haven't moved in a long time. The boulders more towards the left are paler in color, which indicates they've been recently overturned. And in this case, they were overturned in the winter of 2013-2014 during the severe storms of that year. We're going to look in a bit more detail at this area here, and the boulder that the yellow arrow is pointing at is the boulder that the yellow arrow is pointing at here, with one of my students sitting on it for scale and its location, its identification number that she's holding up. That boulder weighs about 2.5 tons. It sits 26 meters above the high tide, and it is currently about 11 meters inland of the nearest cliff edge. And we took this picture in June of 2014. If we juxtapose it with an image that was taken of the same field of view a few years earlier, and here I've put in some yellow arrows to show points of identity to help you orient yourself in the image pair. And you can see that there are a number of differences between the two images. So as you scan your eyes back and forth from one image to the other, you can see that there are a lot of pale gray clasts in the right-hand image that are not in the left-hand image. You can see some of the darker gray clasts are in different positions, including some fairly large ones. And we noted at this site that boulder transport had occurred as much as 25 or 30 meters from the cliff edge. To give you a couple of specific examples, there's an empty space there in 2011 that's occupied by a sizable boulder. This one here is about 1/3 of a ton in 2014. And you can see even back as far as the image goes, there are smaller clasts that have been transported that far inland during those storm events. We can take those observations and translate them into fluid dynamic information and derive the horizontal flow velocities that were active on those cliff tops at that time. And to do that, we think about fluid dynamic equivalencies. And there's lots of different sorts of equations that you can use to estimate the initiation of motion criterion for boulders. Here's a nice one by Nandasina that gets used a lot. And it's a lot of variables, but it's a fairly simple relationship. And what this is saying is that the velocity, u, is a function of a number of boulder characteristics: the density, the size of the boulder, its shape, the relative sizes of the 3 axes, the characteristics of the flow that moved it, its velocity, the drag it exerted, the lift forces, and something about the terrain. In this particular case, the slope is what's used. And then some of these terms are a little bit like fairy dust because the coefficients of lift and drag that occur there are not that well characterized. So for that reason, we can't claim that a velocity we would calculate with this equation would be a precise velocity, but we can think of it as an index velocity that gives us a sense of the amount of energy that it would take to move a given boulder. So if we apply that equation to these boulders at the tops of the cliffs near Dundukahar, we can conclude that it took about 4 meters per second flow velocity to move that 2.5 ton boulder at this location at that time. And I'll point out here that the storms that moved these boulders were strong storms, very strong storms, but they were not the most extreme storms in terms of wave energy as based on meteorological characteristics. These were storms with probably a 10 to 50 year return interval. So to put this in context, this is not the Aran Islands, obviously. This is Highway 90 in the US as it goes over Bay St. Louis in Mississippi. And this is the same bridge in 2005 after Hurricane Katrina had passed through. And the slabs that make up this bridge are boulder analogs, if you like. And a couple of years after the hurricane, some civil engineers did a calculation in which they determined that the velocity of flow required to do the damage to the bridge and move these piers and slabs from the deck was about 3 to 3.5 meters per second. This gives us a comparison with the Aran Islands. And so in this graph here, where I've got flow velocity, nominal, the index flow velocity on the y-axis, the big thick red line is that range of velocities from Bay St. Louis. And I'm going to plot on here now data not just from the area near Dundukahar, but data that we collected from throughout the Aran Islands. at a range of elevations from sea level up to 26 meters above. And you can see that the highest flow velocities that we recorded as a result of those storms were about 10 meters per second at fairly low elevation. This particular boulder was a 620-ton block that moved on Inishmore. But here on the tops of these 26-meter cliffs, and this includes the Dún Ducahar site, we had flow velocities of at least about 4 meters per second. Those 4 meter per second velocities are greater than what it would take to knock out an interstate bridge in crossing a bay in the US. So relating these to these coastal heritage sites in a little bit more specific detail. So here again is Dún Ducahar. And here is a lovely map showing the structures at Dún Ducahar. Claire Cotter gave me this, and if anybody knows where this was published, I would love to be able to credit the author and the specific publication. And what I've done here is I've taken a drone image and a nadir image looking straight down at the site and superimposed the map on it. And here, whereas we focus usually on the main enclosure wall and the reconstructed remains of the buildings within it, there are these indistinct structures that are out beyond that wall. And when Claire told me about them and showed me this map, I was like, you're kidding me, because I've been there and I didn't believe that there were structures there, because this is what they look like on the ground, where wave-moved boulders have overridden those remaining structures, making them extremely difficult to distinguish. But you go out there, I went out there after she told me about it, and yes, I believe they are actually there. But they have been heavily modified, and they are in the process of being eradicated by these boulders, which are still on the move. We measured these boulders that are flagged here, moved again during those storms. So the upshot here, and kind of take-home message, is that high energy sediment dynamics can tell us a lot about what's going on at some of these sites. And that if we map them and track them and pay attention to them, that it gives us good numbers, strong indications of the sorts of forces to which these sites are subject on a fairly regular basis. And knowing the kind of flow energy that impacts the walls of these coastal sites can be used to develop risk assessments as a component of long-term management of these sites.